uh, we will get started with hardened properties. So until now, we were focused on building or constructing a 3D printed concrete member. And in most of the cases in regular concrete, you wouldn't talk about what we did for the last 3 days at all, correct? It's only the hardened properties that matter. We all know how to mix concrete, pour into some form, it'll do its own thing, harden and do all of that. But in this case, you can't do it, and that's why we spent disproportionately more time on fresh properties, on rheology, because without that, these 2 days doesn't exist. Whereas in conventional concrete, you can do some jugaad and you can still get your concrete and get stuff happening. Whereas in this case, you just will not be able to get something buildable and layered up to a height, to a size, to a dimension that you want. So what we talked about extensively over the last 3 days was characterizing the material that you want to use upfront for its rheological properties, correct? Which means you look at the binder and the binder composition that you want to use, particle packing effects that come along with that binder composition, aggregates if you're using them and how aggregates pack themselves. And when you do the rheology, when you do a rotational rheology, when you do a flow testing of those materials under strain rate or stress growth or whatever protocol that you use, what characteristics you get. That's your basic material properties. You take that material then, and then you lay it into a form. You have to extrude it through an extruder. That is the process that we talked about for a significant length yesterday. And that process influences the properties of the layer that you print, the layer dimensions, which in turn is determined by the velocity and all of those parameters. So all of those interrelationships are what we talked about. In this, we did not do one thing, which is no different at all from conventional cements and concrete, which is the hydration part. While we talk about the material structuration, gaining strength, developing, thixotropy, all of this are implicitly assuming the fact that cement and the other materials are reacting and hydrating. That's a totally different course. Once we get there, we'll have to go that rabbit hole for such a long time. So we are not even getting into the idea. We are saying now magic happens, you have a strong concrete. How does concrete gain strength? I'm sure you would have done in other courses, cement hydration, property development, lots of associated stuff, correct? So we are not going to get into all of that, especially with these multiple materials, with rheology controlling admixtures. Hydration is quite a bit different. The way in which the material develops structure is quite a bit different, but that's part of a different story. Having built a few layers up, having built a wall, now I want the wall to perform adequately for the rest of its life. How do I evaluate that? So, one of the fundamental ways in which you think about concrete is about an interrelationship between three different things. Okay? One is a material microstructure. Second is a material processing. Third are the material properties. So if you look at any materials, if you talk about material science, these are the fundamental aspects of material science of any material. This is the classic trifecta. Microstructure, processing, and properties. This is like three legs of a stool which interact with each other to support everything else that you do, right? So you need a good, well-developed microstructure for which you need materials to be rheologically consistent, materials to hydrate, all of that. To get to that microstructure, you need a level of processing. If you talk about conventional concrete, you need a good level of mixing, good way to place it, good way to cure it. Those are all the processing part. Correct? So and that develops a good microstructure, which in turn will give you better properties. So structure, processing, properties. with respect to 3D printing of concrete, the processing is what we did for the last 3 days. Everything with respect to rheology and extrusion and layering is about the processing. The printer now has no more role, correct? The printer is out of the picture. It has done its job, it's gone. Now it is about the structure that you've built up. Then the structure has a certain the whatever you've built up has a certain microstructure, and that influences properties. Is this idea clear to all of you? It is that link, and this is not just for 3D printed concrete, any material, whether it's concrete or steel. All of you have done some class on processing or manufacturing of steel. You know how steel is manufactured, right? So you have iron and carbon, both are heated to a high temperature, and you cool them differently to get different types of steel, right? Whether it's a martensitic steel, perlitic steel, and then you use different types of alloying materials, whether it's stainless steel, you use nickel and chromium, it's a high carbon steel, you use higher amounts of carbon. So all of these alloying and the cooling processes that you get to the type of steel that you want are all the processing parts associated with steel. And once you take the steel, cut and polish it, look under a microscope and say, oh, I see perlite colonies here. Oh, I have austenite here. I have martensite here. That's its microstructure, right? And then when you want a high strength steel, you say, okay, what's the proportion of whatever alloying compound you did? That dictates the properties of it. Whether you have martensitic steel, whether you have austenitic steel, whether you have perlite, if you have lots of cementite, you will have a brittle steel. If you have lots of perlite, you have ductile steel. That's a microstructure that determines the properties. Correct? So in that same vein, in that same idea, now if you want to do, if I'm teaching a undergraduate class where students really haven't been exposed to materials, I give them examples of food. And in the US, or in general in the Western countries, everybody likes to eat steak, right? And when you go to a restaurant and order steak, they'll ask you, how do you want your steak? Whether you want it rare, medium, or well done. Rare is not very well cooked at all. Some people like that. Medium is kind of medium cooked. Well done is really well cooked, right? So rare, medium, and well done are processes that you impose on this material to get what? To get the kind of taste that you need. Taste is the property that you're looking at, right? So some people may like well done, some people may like rare, but that's the property that you want. You process according to the property that you want. And the property that you get is a result of processing. All of this is done on a material, right? If the actual steak material that you get is not good enough, none of the other things might turn up the way you want. Correct? So again, all of these things. And what does processing need in terms of material, in terms of cooking, for example? If cooking is a process, what are the variables that you have in cooking? Temperature and time and heat is temperature and whenever you hear the word temperature, what comes along with it? Pressure. Every time your fundamental PV is equal to RT. Remember that? Your Boyle's law starts with pressure and temperature relationship. Pressure cannot coexist without temperature. You guys pressure cook? You pressure cook at ambient temperature? You say that you put stuff in the pressure cooker and just leave it here, it gets pressure cooked? Pressure goes with temperature. It has to go with temperature, right? So any processing is a function of pressure and temperature. If you look at manufacturing of cement, it's a temperature induced process, right? Of course, there's no pressure, it's ambient pressure. So all of these processes are what we use to end up with a microstructure that you want, with the understanding that a good microstructure will in turn give you good properties. So far clear? So now we'll get into 3D printing of concrete and see what happens. I have done all of these yesterday. Oops. Did somebody fall down? Okay. So we did this yesterday. This is your conventional mold casting. Instead of doing this process, we decided that this is what we like to do, correct? We are now putting things in layers. Simply look at this cross section and this cross section. What can you see? Homogeneous, inhomogeneous, correct? So very quickly, I did all these 3 days of work to study all the rheology, complicated work, and now you're telling me that I'm getting a crappy microstructure here, right? Um, Certain things you have to figure out a way to solve it. So this is homogeneous. This is why we love concrete in a cast form, right? If you get cast it and then you figure out that it was not coming out properly, no problem. Bring a vibrator, vibrate it once more. It'll all be good. And you've already anyway over designed it for if you want 30 megapascal. You remember your concrete mix proportioning when you want 30 megapascal, 30 plus 1.36 times the standard deviation you add to account for the guy who screw things up in the field, for the cement that might not come out okay, for the curing that you might never do. You account for all of that and you eventually end up with a 40 megapascal concrete and you say, okay, I want 30, I will need 40. You ask the ready mix supplier for 40, he will give you 45 or 50. Right? You end up always with a higher strength and higher properties. So, and here is my point. If somebody says that a concrete bridge has collapsed and they do strength test and the material did not gain strength, how many times you should have screwed up to get that? It's humanly impossible. Sometimes I tell students to get a C or a D in my class, you have to work really hard. If you really come, listen to class, do the work in the class, you will get an A or a B. To get a C or D, you will have to work really hard, right? You have to work the other direction. You have to unwork really hard. That's what, if even if you do all the regular stuff okay, you will get good concrete. So if you say that I designed for 30 megapascal and then a year later somebody drills a core out of it and gets 10 megapascal strength in concrete, somebody has worked really hard to not to put the cement and not to cure and do all of that, right? So what we end up is a good quality finish, good quality material generally. Now, because of why did we go from here to here? Why did we go from a mold cast to 3D printing? Why were you all here? What was the interest of all of you in coming here? Hmm? To remove the idea of form work, right? What happens with form work? I am getting a rectangular shape most of the time. Any other shape, I will have to spend a lot of money on the form work upfront, right? So I want to now get away from form work so that I can use whatever shape I want. I'll have flexibility in shapes. I have flexibility in construction. I don't need a more form work. I can build things up quickly. I can do rapid construction, all of that. But then if you want to do it then layer by layer, this is what happens when you stack layers. So even when you extrude a layer that is rectangular, when it gets to extrude, the material will settle down, material will slump, and naturally you will start to get beveled edges unless you have a brick type extrusion, which I showed you yesterday, for which you need an extremely stiff mix, right? And that also has its problems. So generally, you will get bevels, you will get curves on the edges. Why do you get curves? There's a very simple explanation that when you put things on the ground, when you lay things, and when there is gravity, your edges tend to curve around and you get that kind of a shape. The material allows itself to mold it that way. Now, if you ask a physicist why does things curve, he will tell you that a curved shape has the lowest energy and materials would always like to go down to the lowest state of energy and therefore it is naturally following its path. Like water goes to its lowest potential from a higher state of potential to a lower potential, right? You guys also would at the end of the day would like to go and sleep. You would want to be in a lower state of energy, correct? And how do you sleep? Standing up and sleep? How do you sleep? You lie down and sleep. Why do you lie down? Have you ever thought of why am I lying down when I sleep? Huh? The energy is minimal when you lie down. Why? Simple. Now there is gravity acting. I'm a concentrated load. I'm a uniformly distributed load when I'm lying down. Simple. Your structural analysis, your statics will tell you that's the lowest energy, correct? So every material would want to go down to its lowest state of energy, and therefore, and that's why Earth is in a spherical shape. Otherwise, Earth would be some cuboid or some fancy shape. All planets would be all fancy shapes because nature would want everything to go down to lower state of energy. Why do two elements combine to form a compound? Because a compound is a lower state of energy, right? So that naturally you will get an energy criteria there. But then the problem is if I have only one layer, I'm okay. But what happens if I put the next filament next to it? Now I start to develop voids in between filaments, right? So this is interfilamental voids, if you want to really call it. Sometimes people call everything a layer. This is a layer, this is a layer, this is a layer. All are layers, you get confusing. So you ideally call whatever you're building up in the vertical direction as layers and whatever you're putting in the horizontal direction as filaments. So that makes it a little easier to understand. So this is a layer, this is a layer. So this is the layering direction. These are all filaments, and therefore that's a filament direction. Correct? So you can do that easily. And then so you have interfilament voids. So you will see voids like that, interfilaments. Now, do you think these things are also perfectly solid? Well, you would like them to be perfectly solid. You will do whatever you want to be perfectly solid. But remember, what is that you are doing very easily in concrete to avoid air voids and defects? Vibration, correct? You vibrate it. Why do you vibrate? Just so that everything is uniform and no air voids. Are you vibrating in 3D printed concrete? Then it'll be fun if you vibrate this also, right? So you can't vibrate, therefore you will end up with these layers and these discontinuities. So you now have effectively two kinds of discontinuities, one within a vertical layer, different layers, and one horizontally as you move from filament to filament to filament. Correct? Now, if I cut a piece of concrete from this one, do I really care which direction I test? No, right? Because you have poured it, you have also all homogeneous isotropic. How about this? It's going to be extremely dependent on which direction you test. Now, what does a 30 megapascal concrete mean? Here, 30 megapascal concrete means everything that's inside here. What does a 30 megapascal concrete mean here? A piece that you cut and orient it in a certain direction, test in a way that there is only two filaments in one direction and only one interfilamental join, and there are only 6 layers in it. You have to write an essay before you say what the strength of your concrete is. Do you think the guy in the field actually will understand what you're going to say? You're going to have bigger problems now in terms of qualifying the material. How do we overcome that? Do we have complete solutions? No. But can we try and find out ways to overcome that? Can we at least think about ways in which we can design to mitigate this? So those are some of the ideas that we'll talk about. Now, one more thing. Remember, this is the extrusion direction. So the printing is happening in this direction. Correct? The materials are being printed in this direction. Layers are being built up in this direction. And there is this direction also in which all these layered voids are there too. So you have really 3 directions to take care of. Okay. So layer and interface effects, the same ideas I told you. Now, if you actually do it, and this is what you will see, that these are all the interfilamental defects. You see all of them, all of these defects where this filament joins this filament here. So there's one layer, one layer, or sorry, one layer, one layer, one layer. So all of this, in between all of that are the interfilamental joints. And then in the layers by themselves, you may have voids as well. So all of these very interesting ideas, which means if I want a higher strength, you saw the bridge yesterday and you saw how it was printed, right? You printed it and then flipped it, which means before you print, you should know how the bridge is actually going to be in the field so that you can print in the direction along which you want the highest strength. That planning has to go in randomly. You can't print a shape. The printing path and the print direction has also to be accounted for. Okay, so interface regions contain characteristic pore systems that govern transport and mechanical weakness. Transport durability is generally when you have ingress of moisture ions. Generally, if you have reinforcement, it is for a corrosion dictated phenomena, but then lots of other things also can happen. You can have leaching, which is also because of porosity. You can have sulfates, and you can have uh, lots of other deleterious stuff go in and cause problems. So again, voids are always bad things to have. Um, Interlayer regions are as locally more porous and better connected than the filament cores, indicating preferential paths for cracking. So you hear these are the interlayer interfacial, interstrip, that's the interfilament regions. And then in between all of that, you might have some defects and some macro pores that might happen. So to look at moisture transport and interlayer formation. Now, remember, as you have a layer that you're putting, again, we said, okay, we put in layer, now it's all hardened, now we are looking back. But all of these processes that you are seeing now are also the result of what you were doing while you were constructing this. So you think about a layer. I put in a layer while on top of this layer, while this layer is wet, versus I put a layer on top of it while this layer is dry. What do you think the differences will be? Placing wet on wet versus dry on wet or wet on dry. Hmm? Wet on wet will have better bonding. You can have, hydration products form between the layers will have better bonding. If you do wet on dry, that's a cold joint, right? Now you'll have to figure out how to account for cold joints. Now think about it. Go back about the printing paths that I was talking about yesterday. If you're printing in the lab, only a little rectangular thing doesn't matter. But think about your printer that is on a big gantry. Robotic arms also have a limited path of activity. You can control that better. But when you do gantries, these gantries are probably 10 meters long and 10 meters wide. They're on a rail. So they are keeping on putting material in. When will I come back and put on top of it if I don't know? And if I don't know the properties of the material that are developing, I will invariably end up with cold joints. Think about 10 layers or 20 layers you're constructing, and layer after layer after layer if it's a cold joint, right? That is a massive problem when you have larger constructions, when you do very large prints. Assume that somebody told you, I need this very fancy Fibonacci spiral to be built for an architectural structure or whatever. So your printer is going and tracing all these different curved paths and coming back after all of those. And while you have all these curved paths that are obtuse curves that turn around like this, your printing speed has to be different. You can't print this way and a curve in the same way, like you same way as you drive. Like you can't drive on a curve at the same speed as you drive on a straight road, correct? So you have to do that. And because on a curve, the material might tend to follow. You will have buckling and plastic collapse much faster. You'll have to think about all of that. While you do all of this and come back, you might have had a cold joint already. How do you account for that? So printing parts become an important idea in this. So here is a hardened element. You put an overlay on that. You get an inner interlayer. When you have some moisture, you have no moisture. When it is completely dry, how does all of this happen? This has effects in shrinkage, in moisture transport process, all of that. So you remember the other thing. In a form, if I'm putting concrete inside a form, pretty much my entire concrete is protected from early age shrinkage evaporation by the form. Now I have none of those. So in addition to a low water cement ratio that you start to use to make sure that the thing is extrudable, you have evaporation effects much faster because your surface area is much higher, and that's why you see random shrinkage cracking in 3D printed concrete, especially when the humidity in the environment is low. So that's another added complication. Now, When I tell you all of this, you will think, yeah, why bother all of this? This seems to be a big problem. Let's not even worry about it, right? Um, but having done 3 days of rheology, you can't go back. Why did we struggle so much with rheology? Now we'll have to do something to solve this problem. So at least let's try and see where this goes. Um, Testing wise, how do you do the testing? Typically, between layers, you can do direct tension. You can do a modified direct tension because you know that you have some wedges. So, how do you do a modified direct tension? You can do a split tension. This is something that you can always do easily by applying a compressive force at the interface. You can do a split tension. You can do a wedge splitting. You can do one interface shear, you can do two interface shear, you can do Z-shaped shear, you can do slant shear, you can do torsion. Your testing methods, you can go have a party with it if you want to know what kind of testing. So again, it's a very ripe field for research. Not much of work has been done on what happens with all of these effects. How do you do interlayer, interfilament effects? What levels of shear strength do you need in the interface? All of those are still not well known. But you can do all of these testing. The advantage with all of those is if you have a basic testing machine, a universal testing machine that can do tension and compression in your lab, all of these are very simple. You can modify your specimen shape and your support conditions, and you can do all of these tests fairly easily. And you can get interlayer parameters as to what will be. Slant shear, very commonly done. You do lots of slant shear testing. Anybody who does any repair material testing, you always do slant shear testing, right? To find out if the repair material bonds well with your old parent concrete. Very same idea, you can do that. Parameters affecting the bond. Again, I can go back to that same thing that I said. You know, you can never go wrong in this. What are the parameters that are affecting interfacial shear? Everything that you can think of in terms of your binders, in terms of your environmental conditions. Now, interfacial treatment is different. There are people who do, if they suspect that I have an extremely long print path and you have cold joints, you have, after a layer is coming, somebody will go and spray or coat some kind of a bonding agent between layers to get better bond. So interfacial agents, rheological behavior, we did all of this yesterday. Post structure, roughness, bonding area, hydration products, all of that. And then all these printing parameters that we talked about. So this is kind of a picture that brings everything together. The materials that we talked about, the material properties that we were talking about, the printing parameters, the environment, interfacial treatment, all of those different things, and how that affects interfacial bond. Because interfacial bond is basically the bond whether between two layers or between two filaments. So here is something called the filament interfacial zone. So this is the interfaces that you can see here. And if you do porosity as a function of depth, you see here, not much of porosity, but suddenly increase in porosity. So if I take, sometimes this is not visible to the naked eye, right? So we understand that. Now, if you cut from a reasonably well printed concrete, if you cut a piece of it vertically and look at it, if you have done the work decently, you will not be able to distinguish it at all. Okay? So this is an exaggerated picture from a microscopic point of view. With your naked eye, you will not be able to identify. If you have done it well, you will not be able to identify the interfilament. You will still find interlayer. It's very difficult to find out unless you look at it very closely. That does not mean there are no voids there, right? The voids in the concrete are much smaller than your naked eye can see. So there are voids. And if you look at microscopically, this is what you see. Each layer you can pick out based on. So you don't even, if you don't know what the layer thickness is, you can simply do a microstructure analysis and do a porosity analysis. You will know what the layer thickness is, correct? So you will have higher porosity. Now look at what the difference is. And here is what I want you to focus on and understand. You're normally looking at around 5% porosity in the bulk of your concrete. You see that? And when it comes to interface, what happens? You look at 30-40% porosity. You have 8 times the porosity in the interface than in the bulk. What is a ramification? Whatever I do to make my bulk great is useless now in terms of properties. You see that? I spend a lot of time and effort and money in densifying the microstructure using silica fume, using fly ash, using hydration enhancing agents, using viscosity modifiers. All the drama that I use is wasted because a chain is only as strong as its weakest link. You end up with layer joints, discontinuities, which have an order of magnitude higher porosity. Everything else you do with material design, everything else you spend time on developing the best possible mix and creating a high strength mix in the lab goes out of the window because your material now is becoming completely anisotropic. Your isotropy is gone. This is by far the biggest challenge when it comes to mechanical properties. Good? So everybody understands the reason, right? So this is what you see. And then if you want to look at the under a microscope, a scanning electron microscope, and much higher resolutions, and see that's layer 1, that's layer 2, you will see a highway in between. That looks like a rock cave where some animals can creep in and sit there, right? So you will have completely different. So this is the layer 1 and layer 2, and this part, if you zoom in, this is how you will see. So it's a porous transition regions containing interstitial voids, all of that, that can promote fluid ingress, that's one thing, but also promote anisotropic cracking. Because you're expecting, remember, your concrete is a isotropic material, which means you want everything to be randomly oriented. Anytime you have directional consistency, you have a struggle, because now you have to define your strength as a directional quantity. Not that this is not done in the world. Aerospace guys do it every day. They love doing it this way. Otherwise, they will waste a lot of material. And, in an airplane, they can't afford to have 5 tons of weight just because of that, right? They want the airplane to be as light as possible to fly, which means they want strength only in the directions that they want. Otherwise, you can really have a matrix alone. The fibers are oriented, composites, fibers are oriented in the directions that they want, higher properties, higher strength. So this is the idea of defects. Now, remember the lubrication layer yesterday, right? So I showed you, and I did not explain this in detail yesterday. I simply said, if you remember that picture yesterday I showed, if you have a layer, the outer edges of the layer, because of the way it gets extruded, are rich in the paste part or the liquid part. Correct? All of you remember that? Now what happens when you put two of them on top of each other? You have now 2 times the thickness of the interface, where the lubricating layer has a massive effect on the properties. Was lubricating layer good enough for us yesterday? Good for us yesterday? Good. Was it good or bad yesterday? Good. Why? It helped you extrude consistently and nicely with low energy. Is it good today? No, I don't want it really today, right? Now see the conflict between extruding and the properties that you want. It's not that I don't want any lubricating layer at all, because having a little bit of that helps me to attach wet on wet better. But I don't exactly know what's the depth of the lubricating layer I want, which means you end up with, like I said, you end up with a little bit of a zone where you will have a higher water cement ratio, a higher water content, that you will end up with a higher porosity, and the same idea here. See here, that is your core and that's your skin from the lubrication layer, which has a higher void ratio. What does that correspond to? That corresponds to this zone, that corresponds to this interfacial defect. So what was good yesterday suddenly becomes not so good today. But while you're extruding, getting a good shape and getting all the filaments and getting the shape stability, getting the buildability was important. And then you say that, okay, I may have to live with it tomorrow. How do I control that? So again, you need a balance in you. How do you want? So maybe extruding it with a little bit of difficulty is probably not a bad idea. You don't want too much of a a fluid layer. So again, cast concrete versus printed concrete, and you see all these porous joints, same idea that I showed you earlier. Particle migration was processed. Remember the particle migration story that I told you? The same thing that goes with the lubrication layer. Because there is shear at the wall, particles migrate away from the wall. You have a higher particle concentration, and that higher particle concentration is letting you a plug flow go through in your pipe, right? That particle migration. So if you do X-ray computed tomography, X-ray tomography of a piece of concrete between these different layers, so you can see a scan of core and the interfacial zone of small specimens here. And here is a distribution of sand sizes. And which one is this? Yeah. And then the other one is what I have. But here is the pores in the core. These are the pores in the core. And you see the number of pores in the interfacial zone, way more number of pores in the interfacial zone. Correct? If you look at the frequency of pores and the diameter of pores, and then if you look at the anhydrates in the core and the interfacial zone, you will see larger amount of anhydrated material in the core, obviously because the core has lower amount of water than the interface. You get that lubricating layer idea? And as you get closer and closer to the interfacial zone, you have smaller diameter, smaller size of anhydrates. So you go more into the core, you will have more anhydrated material, and you will have more porosity in the interface. So micro-CT analysis revealed that interfacial metal was finer and less porous than the filament core, confirming shear-induced particle migration. So again, particles alone migrate, densification of the core in the particle idea. So again, people have done some really interesting stuff with Raman characterization of the interface to see what that is not very important for us. Simply to say that because of there is more water in the interface, you will get more hydrated products in the interface. But the problem is you get more hydrated products in the interface, but effectively because there was more water, there is more voids and more porosity as well. So SEM, EDS, Raman analysis of, so that's what happens in the interface and looking at different materials. Nothing of interest. Now, layer interface microstructure and local water uptake, you can see that in certain areas, you can see suddenly that you see very, very wet spots, local absorption because of certain voids being much more porous. You can have air-induced cavities, partially healed gaps. You see all these pictures, right? These are all much more close-up pictures of interfaces. Again, going back to the same idea, you will have an interface that is effectively weaker, and I have explained 10 different reasons why that is so. Both from an extrusion point of view, as well as what happens when you layer materials one on top of the other, both in a vertical direction and arranging filaments horizontally. Filament interfaces versus layer interfaces. I mean, you can do geometry, you can control geometry, you can reduce those interfaces. Like I said, vertical interfaces are very difficult to see with naked eye, whereas in a microscopy, you can identify, and as I showed you, you have about 5, 6, 10 times more porosity on the interfaces than on the local zones. Again, void morphology in cast concrete versus printed concrete. You can see here visible air voids at the inner layer. Some of those you can really control by doing good mix design, good compaction, doing what everybody does, a nozzle overburden pressure, making the nozzle squish the layer a little bit while it flows so that your depth of the layer is slightly smaller than the width of your layer when you extrude out of a nozzle, so that overburden pressure just squeezes it a little bit and gets, because you can't consolidate in any other way, this is a secondary way of doing a little bit of consolidation to get the layer effects taken care of. You can do some of that to do it. But again, there's lots of work on X-ray computed tomography, looking at void distribution within concrete. The idea is to show that while in a regular concrete, your voids will be uniformly distributed, now you will see preferential distribution of voids in the inner layer zone. Not that the bulk has become much better. The bulk voids will be there as the bulk voids. But then, like I said, there is no point in making the bulk really, really, really good if you can't control the interface. Because at the end of the day, a chain is only as strong as its weakest link. The interface will fail. Here is again another way to look at porosity distribution, and there are some very interesting work to show that the void shape in the interfaces are spheroids. They're not really spheres. They are stretched spheres. And there is some very nice work to show. I mean, why are they important? Because the shape of the voids will dictate the direction in which cracking and failure will happen. So, especially when you have an anisotropic material, the shape of the voids with respect to the direction of the loading will dictate how the cracks will propagate. So if you've taken a fracture mechanics class, you would know that if I take a piece of paper, take a slit, put a slit in this direction, and then if I pull it in this direction, the crack will open perpendicular to the direction of the applied load. So the stress that is required for the crack to open in this direction is so much smaller than to open in this direction. Correct? So the size of the shape of the void with respect to the direction of application of the load will determine how your specimen will fail. So that's again another consideration. That's why people are focusing on what are the shapes of the voids. There are lots of advanced work with CT scanning. Again, CT scanning instruments are fairly common. Pretty much every university has it these days, and you can do some interesting work with those kinds of testing. Again, difference between bulk and interlayer regions. If you see that's a bulk, so if you take a piece like this, you will quickly identify where the interlayer is, right? You can see where the interlayer is. And remember image J that we showed you? These are all image J images. So if you are ever interested, again, some of these things, if you're interested in doing research, are not high intensity works. If you have a reasonably good optical microscope, if you know how to polish your surface in a reasonably good way, you can do optical images, you can do image J, you can quantify layer and bulk effects very easily. This could be, if you're faculty, these are good undergraduate projects that you can give to your students to understand what's the difference between. So you can print with different mixes to see what the layer differences are, overburden pressure are, how much porosity that you're getting, what does different mixes do. These are good examples for kids to understand the implications. Master's projects, good master's projects too, which can be done in a few months' time. And ImageJ is freely available. It's such a powerful software. National Institutes of Health in the US made this software about 20 years ago, but they've been consistently improving it. It's become as good as any commercial image analysis software now. You can get it free, you can download it, you can do a lot of different things. They did it initially to do blood platelet counts and things like that. But it's now grown into a very useful multi-purpose image analysis software. So these are all, you can threshold it in different ways. You can find so all of these shapes, right? So for the sphere, I told you about spheroidal voids. ImageJ can easily identify void shapes, quantify the void shapes. You can find it out in terms of directions. You can do lots of interesting work. And then if you want to go to the next step, you can start to test those specimens in compression, tension, shear, whichever way you want, and then you can look at the influence of porosity and void sizes on these properties, which are very useful research that you can do. Again, if you're doing PhD in any of these topics, this could be a nice addition to the work that you're already doing also. If you're doing PhD in 3D printed concrete, these are quick things that you can do to add value, and maybe, and we have found this several times, things that we were struggling to explain why this is in mechanical testing suddenly become so very revealing when you actually start to see a microstructure. Things become very quick, and so instead of writing 15 pages of explanation that nobody will believe as to why it failed, one picture will explain it very easily. So if you want to augment your work with these kinds of tools, feel free to use it. Your notes has the link for downloading the software and all of that. With X-ray tomography, you can do three-dimensional distribution of voids. You can see where the voids are distribution all three dimensions. Like I said, if you don't have a three-dimensional capacity, a number of 2D images. And now, okay, let me give you this example while I'm there also. If you take enough number of slices in 2D, there are freely available image reconstruction tools. You saw in image A as well, but there you had to provide all those images. But if you have 10 images, two-dimensional images that you make, for example, like this, if you have 10 images, there are softwares, AI based. So again, if you want to do work on AI, here is another way that you can do it. AI based, freely available software that you tell the software, here are my characteristics. Give me 200 more images like this with similar porosity and void distribution, and it'll give you that. And then you can stitch all those images together in another software. Image also does it. You can stitch all, you can have now a three-dimensional visualization. I don't have an expensive $500,000 3D tomograph in my lab. No problem. I have good optical microscopes. I am willing to spend some time polishing it nicely. I'm willing to spend some time making good images. You can create 3D images to see how your structure will look like. Right? So these are all things that so sometimes if you really don't get good information from 2D, synthetically create 3D images. Lots of fields do this all the time. Synthetic creation of images. Even when we do when you do for medical purpose also, when you scan it, when you do all these different scannings, they are basically stitching the images to get the 3D representation of what is inside. So lots of such softwares. All you need is to look at all of these software is available. I don't really remember off the top of my head, but I can easily find out 10 of these is tools to stitch images and create images for you. So again, if you're interested, these are some valuable research areas that you can do while waiting for other sophisticated instruments, money to buy some of those things. You can do some of this. Okay. What happens to porosity distribution after exposing to the higher temperature? If you want to have 3D printed concrete subject to high temperatures, some people want to use it for example, one of the things that they're looking at is as for solar collectors. So when you have the solar shields, when sun comes in, you want to have all of those shields, reflectors, supports for those solar reflectors. So if you're putting this in the desert somewhere, you can just print a bunch of them using local sand and then put this. So these are supporting structures for these metallic reflectors to capture solar energy, which means these reflectors are being heated to about 600 degrees Celsius, which means the support structure also will be subject to high temperature. So what happens to porosity, pore size distribution? What happens to damage in those cases? Again, porosity distribution, so many different ways to show you how this could be varying. Again, more of porosity distribution from so many different angles, because that's why people are beating this to death now, because it's important, right? To see here, if I look like that, do I see any difference? Now, if I start to identify, I'm seeing those differences where those layers are, correct? From the porosity, I'm able to find out those inner layers, and then of course there are smaller pores. So lots of these tools are becoming prominent, and these are important to understand and explain what the properties of your material are. I'll stop here. It's been almost an hour. I'll stop here if you have any questions, and then of course we're not stopping for tea. We'll stop for tea after another half an hour. But for the time being, I need a breathing break. If you have any questions so far.
Sir, can you take the same relation to phase 3, lubricating layer, water migration is about that today's service?
This one? This one? Or before? Where was it? Okay. So this is with time, right? Simply you're talking about time and see how the water is evaporating. This is your regular cement, regular concrete itself. your regular evaporation from your regular concrete, right? Now, what happens with evaporation from regular concrete is it's evaporating from a bulk. What happens now? It's evaporating from a thinner layer, right? So, what happens? You now have suction pressure from water capillarily to rise from the top. So, what happens? This is standard. So, if you have water rising from so one layer and one layer, your water evaporating from the top and water coming in here, you will have the water tendency to accumulate along this layer, right? So the drying of it creates now a large amounts of entrapped moisture in that layer while this layer is shrinking. Correct? So you might not feel that there is a problem with the lower layer, but this is causing a problem here in the lower layer too, because you have evaporation from that layer. And because it's all surface area to volume ratio is so high, the layers are thinner, correct? Surface area is much higher compared to the volume. The evaporation rate is also much faster. And especially when there's high temperature and high wind velocity, this exacerbates. And so your typical moisture loss calculations that you do in concrete using the nomograms, I'm sure you would have seen with wind velocity and relative humidity and all of that, they won't work because you're dealing with much, much, much higher surface areas. Other questions? All right, if no questions, we'll go to. But you get the general idea of porosity, void distribution, what happens with interlayers, interfaces, and a few tools as to what you can do in your own research if you want to use some of these techniques.
So, when we actually do all this, then we subject to that structure type something outside loads, any loads. Load is not discriminating whether you have a 3D concrete or cast.
Correct.
How do you account for these porosities and all that?
But
the structure actually would fail, rather you are not going to that region where the failure actually is because of the inherent bias that we actually.
Yeah. The load will not distinguish whether it's between 3D printed concrete or not normal concrete. But the difference in the porosity between 3D printed concrete and normal concrete will definitely be reflected in how the material performs against load. If I have a porosity that is oriented and preferential in a certain direction, will accelerate cracking if I load in that direction, right? So overall porosity, say that's the whole idea. You might have and there is lots of work done in this area. Your overall porosity might be the same, but your pore size distribution tremendously affects the failure properties. It's been done in ceramics a lot on failure of ceramics and how cracks and fracture initiates at localized points when you have pores in ceramics. They've done a lot of work. In cement and concrete also people have done work. So yes, overall porosity might be same. So do you think that if I have 10% porosity, I stick all the 10% in this? So that's why strength-based criteria sometimes fail to account for this, right? Strength as a function of porosity. So higher the porosity, lower the strength. But do you think that a void that is thrown in as 10% right in the middle of the body or a 10% distributed in different parts of the body will have the same kind of behavior? The cracking behavior is going to be completely different, right? The crack propagation pattern is going to be completely different. And therefore, that will influence the failure patterns, then and the void distribution will influence how moisture and other ions go into it. It will influence durability as well.
But then there should be some USP of the 3D concrete. Encourage you to go for this 3D concrete as far as the load transfer or the performance to load setting. Because I can see it's quite also any serviceability side also. You have the porosity, large porosity, then we need to see whether the serviceability criteria are satisfied.
No, but you're also now talking about, and that's why. So porosity has lots of different implications, right? Um, it has implications in transport. It has implications in mechanical properties. So you have lots of these different effects. And what we are also looking at now is the fact that porosities are distributed in certain locations, making certain locations more preferential for failure, making the overall behavior of the material anisotropic. Correct? So all of these are aspects that you have to consider. if you are going to be designing a really critical structure. And that is why in yesterday's bridge you saw the whole idea was that the force follows the form. So you're designing it in such a way that you have now much better control of how the force flows through, and you're designing the material exactly in those dimensions. That's a big best advantage. So some of those effects you're already doing it in design, and you do the best possible in terms of material to avoid cold joints, to make sure that the interfaces are not tremendously highly porous as compared to the bulk. You do all of that, and you eventually will get every material development, every in the whole process of human development in materials happen like that. In regular concrete also, even though we call ultra high performance concrete is nothing but a void free concrete. That's what it is, right? By doing all the processes that we do, we are eventually getting a void free concrete. Why is that? Why are we struggling to make a concrete with a water cement ratio of 0.18? While I can mix a regular concrete in 5 minutes, here I mix 45 minutes to get a UHPC done. I spend all this effort simply for the fact that I can get my higher strength. I've understood that I can get a higher strength only if I avoid voids. No amount of high strength cement is going to help me. You tell me type 3, type 5, type 25 cement is not going to help me to get a higher strength unless I take care of voids. So all my effort has been to get me a void free concrete, right? That's what we've been doing. So all the effort, but we don't have to do it to that level here, because you have several other levers you can manage. You have the design lever. You need to put material only where you want. You can put the right material where you want. You have all those levers, but then this layering causes all these undesirable effects. We have to make sure that we control that. There are people actually putting in textile reinforcement between layers, right? So put in a layer, put in a textile, put in a layer, put in a textile, because the textile is very strong and it starts to interconnect those layers. You get stronger layers. But then the question is, now you need another additional effort to put textile between the layers, another additional money that you spend on doing it. And there are people putting in once every 4 or 5 layers textile. Great idea, but when you test them, what happens with which of things between the layers, right? So you can have all of these effects as well. But none of this, again, like I said, the point of all of this is not to solve any of this because people haven't solved it. The point is to point that there are problems, there are approaches that we can potentially try to solve it, and all of us are here. You guys are all working in that area. Maybe we can do all what we can do, our bits to contribute to the process, right?
In the image analysis, like we have shown the porosity distribution. It's how we are kind of calculating the total porosity is based on the pore sizes that so the total porosity is that you have mentioned in the slide.
Yeah. So how do you calculate it? Okay, so there are several ways of doing it. And so there is a whole field of mathematics called stereology. And this is basically playing around with 2D images. So if I have an image and say assume that I have pores like this, right? And if I don't have a concept of area, so this is a 2D image. And if I have several such 2D images, and I know the areas corresponding to all of these voids in several such 2D images, I can say stereologically that that's an average 3D porosity. But assume that I have no concept of even areas. So one of the ways, and this is the first development when the computational tools were not very powerful that people did. So basically what you did is simply drew lines across, right, at predefined spacings. And then, so if this image is say 200 microns, and I drew 10 lines, my total length of lines is 2000 microns. And then I simply count or measure the distance that is in between these pores. This plus this plus this plus this plus this in all the lines. Say that is 400 microns. I say my porosity is 400 by 2000, 20%. This is how it all started, right? So this is one way. So even in the images that I showed, at one cross section, right? So you're doing porosity at one cross section. If I want, that's the way I do porosity. You see that length of the line divided by whatever, that's the porosity of that line. And then so if I have in this image, I have only a few pores here, plus suddenly in this line a lot of pores. When I cut this line, I get a lot of pores, which means that's an interface. I simply, all that you have done at that point is to measure the distance between these lines. And this is image J does it. Even if you don't want to do it, you can write a MATLAB code for an image to do this in whichever way you want, right? So all of this becomes image J sometimes predefines the length of line. If you say that I want it much more finer, write a MATLAB code with predefined with whatever you want. So all of these things are fairly easy to do, and from a research point of view, you get very, very rich data. And again, for those of you who want now, maybe this is the AI age, so I should do an AI pitch as well, right? If you want to say that, oh, I can use all these data that I have, hundreds of thousands of images from 3D concrete that I have made, I can use an AI program to predict where can I find the highest porosity or what pore sizes. So much of data. You can use an AI. You can ask ChatGPT to write you a code for it. It'll write a nice MATLAB code for you to predict all of these things, right? So in terms of research, sky is your limit. There is lots of things, lots of unexplored areas in this that you can make your own. All right. Where are we? I think I'm. Okay. What happened? Can you check this, Vandana? This is it's freezing. It's not okay. It's coming. Okay, let me see. Resume slideshow. Okay, I'll close and reopen it. Not that. Wait, no, not that, not that. It's a different slide, different. Okay, again, we looked at this porosity distribution. Um, Surface texture, porous interlayer, surface texture. So you see here, surface texture also, you will see surface porosities. Shrinkage cracking can cause cracks on the surface. That can cause porosities. You can have tearing on the surface because the way that if the mix is very dry and when the nozzle pulls off, it can tear a piece of concrete along with it, and you will see surface irregularities. Remember, unlike normal concrete, you can't go and take a trowel and finish on the top of the surface, even though some people have done it. There is actually a company who has in its along with a nozzle, it comes with a side thing that finishes that brick that as it lays along. So you can make, but then you need very good flowable mix for that. And that flowable mix, once you make it more flowable, you have much more propensity for interface effects and all of that. So again, it doesn't come without disadvantages. There is something called filament stitching. There are, you see here, basically like you do your clothes. This people do it for fibers. So you can see again, it's a small scale kind of work, but the idea that um, you can, instead of printing in two directions, you can now stitch in actually three dimensions, right? So you can start to stitch the elements. So your print path is this way, then you come and stitch it in a different way. So you get interlocks in between layers to make the mechanical properties much more stronger. Difficult to implement in field, but you can do it. There is lots of work that also says, and that's an interesting take on this, where so I have now layers, and layers are parallel to each other, correct? If I kind of reorient that layers, if I have a path of layers that is different, the anisotropy in the layers will cause blunting of cracks as you get the cracks to that layer. So basically, yes, let me make my interface porous, and porosity, those voids will blunt the cracks and the cracks will not go through. I have a tougher material, right? And this is a field where people have done this for certain polymeric composite materials. Very difficult to do it in concrete, but it's potentially a way to think about stitching the material and architecturally structuring it to give you better properties. So here is stitched filament architecture, and here is exactly what I was saying. You see the crack deflection and bifurcation. The cracks are not going straight. The cracks are along the stitched path, and we have published a paper in similar lines, not exactly this, but you can actually you can deflect the cracks. What happens when you deflect the crack? It is like saying, you know what, this road is blocked, take a different route. Anytime I have to take a different route, I have to spend more fuel. And cracks come with a certain predefined amount of fuel. You run fuel out of them, they can't go further. Cracks can't propagate, we are good, right? So it's like driving the energy of the cracks away by making them drive a longer distance. That's crack bifurcation, or you can blunt the crack. You can, as the crack needs energy to come through, and as they come through, put a hole in the front. All of you have, how many of you have done some fracture mechanics class, some basic fracture mechanics class? All of you, you know the idea of stress concentration of a hole. The idea that you drill a hole in front of a coming crack is simply that the crack loses steam. The crack is confused as to what to do at that point of time. You reduce the stress concentration factor at that area. So all of these techniques you can bring together and create crack deflection, crack bifurcation. Now here, one crack is becoming two cracks, which means it has to partition its energy to two people. It doesn't have as much it had to go the distance that it wanted to go. So you can do stitched architectures to do so many different things. Post structure of printed versus cast sample. That's your cast sample porosity in mercury intrusion porosimetry. That is for a printed sample. So you see about double the porosity, but again, these are all questionable stuff. There are differences. Some people will say double, some people say it's fairly similar, depending on what you see. But generally, you know that when you print them, you are likely to get more porosity. Now, layer height and properties. I think this is what we will spend the next lecture after our coffee break on. But we can do a lot of this. Again, see this here? Just to give you a very quick idea. In compression, I have layers like this versus layers like this. Right? Is the performance going to be the same? It will be very different, right? So we'll look at some of that. And then whether it's flexure also, whether you are doing 4-point loading versus 3-point loading, what happens to cracking, all of that. We'll show you some images. Overburden pressure. Here is smaller layer heights versus larger layer heights. As you increase the layer heights, right? When you increase the layer heights, what happens? I told you the material has a tendency to curve on the edges. As you increase the layer height, that curvature also increases. When that curvature increases, the next one will be like that. You will get porosity here as opposed to a smaller porosity here, which is what you see here. If you have very small layer height, 5 mm layer height, can you even identify the layers here? No. This is just a simple picture, not a microscopic picture, nothing. This is simple, straightforward image. You can't even see the layers, right? Whereas here, you can kind of start to see that interfilament. When you have a layer height of 15 mm, you really have to start to see it again. Your mix can be optimized to reduce some of these effects as well. So you don't have to do this. Anisotropic transport behavior, we will see some of this as we go through with transport as well. For different mixes, the porosities in different directions, not very different in this case. So it doesn't have to be really different. Sometimes you can reduce the anisotropy by controlling how you print and do all of that. Porosity, post structure, we've done all of that. Transport paths. Again, this is a 3D printed concrete, fairly nice. Whereas when you get here, there are super highways for ions to go through. Geometric tolerance is another idea that we talked about yesterday. Tolerance also, if you have two layers, the tolerance between both layers also will start to cause cracking, cause to defects, and of course, you have lack of buildability. So there are simple ways to do tolerances in the lab if you want. These kinds of scanners, Amazon, very cheap. I don't know how much it costs in India, but these are probably $100, $200 ish in the US, fairly cheap. And then you can use those scanners, high density CMOS camera with lasers. You can scan all of these and you can see your error distribution along the printed height. So you can see how well your printer is printing along the height. You can see how well your material is holding up as you print along the height by using some of these techniques, which are not very expensive. Again, all techniques coming from electrical engineering, computer science, vision engineering. This is the technique. For example, when you drive fast or in a road that you're not supposed to fast, they'll take your image, right? The police will take your image at high speed. How do they make sure that the image that they get is actually the correct image and the numbers are not blurred? Taking more number of pictures, stitching them together, processing those images, using tolerance analysis, same kinds of techniques to get what those tolerances are. And you can use some of these techniques as well. And here is another example of different filaments that you have and the tolerances in the flow ratio and the size of the filament. Another way that you use laser triangulation to see where your uncertainties are, where you have bulging. You can see some bulging here, right? And how much of error is there as compared to this straight line, which will tell you how stable this column is going to be. So you can do some of these techniques as well. So I will stop here and take any questions before, and then after tea break, we will get into the analysis of layer effects. Any questions on all of the lot of things that we talked about so far? No questions? Either everything is so clear, or no, I don't even want to say the or part.
So where you can kind of determine this the thickness of this interlayer other than the layer.
Interlayer thickness, once you have cast it, that's probably the most direct way of finding it, right? Cutting a sample destructive way is the most direct way of finding it. Non-destructively, I don't know, but you can always think of methods, right? You can always, we have used electrical impedance always to find porosity. So, hey, is there a way to use electrical impedance to find porosity? Could be, you can. Um, can I think about signals passing through solids and voids and kind of deconvolute those signals and get all of that? Yeah, they're all possible.
Like uh, right now we implemented in this kind of thing, like image analysis is like kind of practical, like implemented in research and all.
No, research and all, plenty of image analysis. Yeah, yeah.
Yeah. Like that, is there any kind of other techniques that people have used for quantifying this thickness of this weak on this about element of what lens?
I can't think of the top of my head other techniques to quantify interface defects, interface thicknesses. But I'm sure somebody would have done something else. I haven't read the entire literature in the field, right? I'm sure somebody would have done it. There might be other interesting methods too.
Question is where we are at the standardization of it is, for example, let's speak mechanical properties. But depending on the filament size, so the minimum filament size we need to test, or whether we go filament wise or some part of the thickness, and then we'll be having different filament sizes.
Correct.
So
Those are all parts of standardization, right? We haven't had that. Correct. We haven't had because the field hasn't grown that fast and nowhere. US, they are now starting to do walls. For example, if you build a full wall, now they have standards. ISO has come out with, the International Standardization Organization has come out with how do you test a full wall. For example, if you want to say my wall strength is so much, how do you test it? So that has been standardized. So the size of the wall that you have to test, how much meter, by what length, by what dimension of the filament should be there in that test. So they have, but that's a still a bulk test. It is still not a material core property. It is still a wall property. So that has been standardized, but we never have gotten to a point where we have an ASTM standard or something that we can follow. For example, you take ASTM C39 to test the compressive strength of concrete. You have a strain rate that you have to follow. You have to, the smoothness of the surface that you have to follow. None of those we have, right? So everybody tests to their own happy standards. Because I don't know that word, because there is a sort of a race everywhere in each country, whether it's towards developing something or maybe towards publishing something. Everyone is going so far, and it means there should be some stopping point. I think consolidate the things and then come up with some standard. Like, no, but so Rylam did, that was what Subbu was telling yesterday. Rylam did a round robin in 38 different laboratories and did lots of tests. What all did they do, Sahil? All compression, all three directions. Um, Flexure, what? It's 4 point loading or 3 point loading? Both. Okay. Okay. Fresh problems. So there are some. Rylam has a committee on this, and they're doing standardization. They're coming up but see, until the standards are and specifications are adopted by the certifying agencies in a certain place. For example, in the US example, I can tell you, if I have to build a 3D printed house in a certain city, this you have to approach the city and they have to accept the code. So if you don't have any code, then it's a chicken and egg problem. They'll say, oh, no code, come back. But I'll say a new material, there is no code, so how do I do it? They'll say, go demonstrate it. So this chicken and egg problem. So what they have done is now you can show this city, if the ISO code is what it is for walls, you can show that your material, your system conforms to ISO code, they let you do it. So there is some kind of standardization for walls. And it is all city by city, so there is nothing that is overall country specific. Cities can decide. But the material kind of testing standards are ASTM standards. Now, this has not percolated there. Lots of times, when you talk about steel, a steel structure, for example, if I come up with a new steel, I come up with a manufacturing process for a new steel today, I have to do the ASTM test on steel coupons and steel elements before I can do a steel column or a steel beam. We are going the other way. We are printing a wall, testing and standardizing a wall, but I have nothing to test here at the small scale because I'll come and say, oh, there is anisotropy, there is layer effects, I can't test this way, I can't test that way, tell me which one way. They say, okay, don't bother about it, test a wall and show me. Right? So, it's which one is right or which one is wrong. There is nothing like that. But every country, every system goes the way they think is more appropriate for them. Right? And there is no reason to follow the same thing all the places, when depends on what is the most appropriate thing that you want to. And there are several countries. China did a lot of these printing even before the codes and standardizations came in, because they said, okay, let's take a risk and do it and we'll figure out what happens. And they were able to do that. And they did a bunch of those. So now they are also getting into specifications and standards pretty heavily, which will be, all of this will happen. It's unlike very, very critical industries, medicines, drug industry, right? You can manufacture whatever medicine, whatever way. You cannot even put one out in the market until this entire standardization by whatever drug agency in that country has done it. But we don't have that way because 3D printed homes hasn't killed people yet. Other questions? Yes. Ask Hanuman. Maybe he can answer. How do you in actual construction avoid interfilament voids? He'll explain. Yeah, when we go to the field in the afternoon, so good segue to for him to show you something special in the field. Good question. So remind him to show that when we go in the afternoon. Stages of using coarse aggregate. Um, so Cobalt, for example, has happily used up to 10 aggregates or even 12.5 aggregates in their big construction. Looks a little ugly sometimes because of roughness and surfaces, but if you don't bother, don't worry, you can use it. Um, I've seen people use 4.75, 6.5 aggregates fairly consistently. And if you get aggregates that are of a good shape, not totally angular and really elongated, um, you get good surface finish, neat surface finish. But it's a big function of what your printer can handle. At the end of the day, it's a function of what your auger, because if you're doing an auger printing, if your aggregates get stuck between the auger, you're screwing the entire process of printing, right? So if you need to make sure that your printer can handle the aggregates. But using the aggregates is actually a good way to do it because multiple things. One, you reduce the cost by reducing the binder content. Number two, aggregates are the most stiff components that you can get in concrete. Some of the deformation effects that you get, the layer slumping deformation effects, is because of lack of stiffness. The stiffer aggregates will control layer slumping and do all of that. The buildability, like I showed you yesterday, is complete function of modulus evolution. Once you have aggregates with higher stiffness, that will help your buildability better, right? So that's another advantage. Aggregates don't shrink. It's a cement paste that shrinks. You reduce the amount of cement paste and add aggregates, you control shrinkage in your concrete. So in all what way you consider, aggregates are going to be better. You have to use aggregates. But why we don't use aggregates and we use mortar only is because in terms of smooth finish, in terms of really nice extrudability, getting it out very nicely, you do that. And there are cases like ultra high performance concrete where you don't use large aggregates because interface effects will cause strength problems when you get to very, very high strengths where you don't even want, um, you know, inconsistencies. So you do that in that cases. But for 3D printing, there's absolutely no reason why we can't use 10 aggregates. And in my opinion, you should use aggregates. Yes. Voids, I showed you, right? Void sizes. Yeah. So if you have, when you print, so some of the work that if you look at some of the recent work in 3D tomography has shown that because you're extruding, normally the voids have a tendency to be spherical. Because you're extruding, depending on the extrusion velocity and depending on the conditions, some of your voids become spheroidal. Some of your void gets elongated, ovalish kind of voids along the direction of printing. So if you look at it, those voids are in the direction of printing, which means if you, so it's in the direction of printing, and then if you apply a tensile load in the direction of printing, you are going to get a weaker one. But generally, you say compression in the direction of printing is stronger. But then with this spheroidal voids, if you get them in the direction of printing, you're going to get them weaker. And you're actually going, if the spheroidal voids are actually in the bulk, you're going to get it weaker than the interface. Right? So now interface is not alone the problem. The spheroidal walls are going to be the problem when you do it. But, I think once you know that there is a potential of having it, of course, processes, doing good mixes, printing it at the right speed, you can always control all of that. Hmm. In their printer, their auger, they have designed it in a way that they can take it. So it's their machine equipment design.
On each of the layers increases, we said like the coverage is also going to increase the each element.
No, as a layer heighting, not the height, individual layer height. Correct, correct.
It's not about the authority, right?
No, it's about individual. So as you extrude, now, like I said in one of the pictures I showed you yesterday, the brick extrusion where you extrude exactly rectangular filaments. When you extrude exactly rectangular filaments, then you need it to be stiff enough to get it in that shape. But generally, we don't have it that stiff because then it'll cause extrusion problems. And you can't extrude that stiff enough material for too long. In 10 minutes, that stiffness is gone. Then you can't really do anything. You can't even extrude. So you do it a little more fluidy. And when that little more fluidy material comes out, they generally kind of curve and bevel a little bit. Other questions? If not, Spandana, tea time. We'll break and then come back and do the